This video is going to look at buffers and buffered solutions, which is section 17.2 in your textbook, starting on page 723. Before I start talking about the chemistry of buffers, let me use an analogy that may help them make sense a little bit more to you. Let's say that in our class, you presently have a 90.3. And you take a test and you totally bomb it. So let's say you get a 50 or lower. And because tests are 25% of your grade, that 50 is going to cause this average that you have to drop. More than likely, it's not going to cause you to drop out of the B range, but what it might do to your overall grade at the end of the semester because of your 5 points added on is you're not going to end up with an A, you're going to be stuck with a B. Then Dr. Quick and I decide that everybody's grades are kind of tanking after this test, and so what we do is we give you a project. And this is a 100-point project, and as long as you do a good job on it, you're going to get a pretty decent grade. So you do this project and you get a 97. And we decide to kind of buffer your grade. We're going to put this 97 in as a test. And this 97 kind of buffers or negates the effect of that 50. And so what happens is your grade comes back up to that narrow range that you're seeking or that you want. Buffers do the same thing in a solution. What they do is they are resistant, well, sorry, didn't want to go that far. They are resistant to changes in pH. So kind of like grades that are resistant to changes in your overall grade. So buffers prevent extreme swings in pH, even when you add a strong acid or a strong base. So you know what grades are. What are buffers? They are solutions of a weak conjugate acid-base pair. And so if we're looking at the components of a buffer, a weak acid and its salt, or a weak base and its salt. So let me give you an example of each. Let's look at weak acid and its salt. So the weak acid is, let's say, acetic acid. And then its salt, you're going to have your common ion that's going to be present. So if you think about what the conjugate base of this would be, you're basically taking that hydrogen away to end up with an acetate ion. So this acetic acid and the acetate ion is your buffer. So it could be sodium acetate, it could be potassium acetate. Doesn't really matter what the cation is as long as it's a weak acid and it's conjugate, and we call that its salt. Weak base, let's say ammonia, and then we want its conjugate acid, which would be ammonium. And so ammonium is going to be the common ion, and that's also considered its salt. So it could be ammonium chloride, ammonium nitrate, the anion's not mattering so much as the weak base and its conjugate acid, or the weak acid and its conjugate base. Okay, so with that in mind, now what I want to do is I want to look at example. So which of these following conjugate acid-base pairs would not function as a buffer? Okay, so if we remember that buffers are going to contain our weak acid and its salt, which is its conjugate base, or a weak base and its conjugate acid, let's look at these. So this first one, remember this C double bond OOH, that's a carboxylic acid. And this is not part of hyperhickel high, honohickel low, H2SO4, so this is a weak acid. Now, if we removed a hydrogen from this, we would get this acetate anion, so this would be the conjugate base. So because you have a weak acid and its conjugate base, this first pair would make a buffer. Okay, so now we want to look at the next pair. So in here we've got the bicarbonate or hydrogen carbonate ion, and then we've got the carbonate ion. So let's look at this one first. Not part of hyperhickel high, honohickel low, H2SO4. So this could be our weak acid. If we remove a hydrogen from it, we would get the carbonate ion, so that would be its conjugate base. Now, if they had listed it the other way, let's say they had listed it this way, where carbonate was first and then bicarbonate or hydrogen carbonate was second. We would look at this and we'd say it's not an alkali metal or a scab hydroxide, so this would be a weak base. And then if that base gains a proton, then you end up with your conjugate acid. So it doesn't matter which way we look at these. In this situation, again, that is also going to be a buffer because you have the weak acid and the conjugate base, or the weak base and the conjugate acid. Okay, let's look at this last example. So let's bring that down here because I've scribbled so much up there. So I've got nitric acid and I have nitrate. Okay, I'm going to look at the acid first. If I think about my strong acids and strong bases, nitric acid is a strong acid. If I think about my strong acids, hyperhickel high, this is the HONO. So this is a strong acid. So this, because it is not a weak acid or a weak base, that pair will not function as a buffer. So basically you're looking, do I have a weak acid or a weak base and its conjugate acid or conjugate base? If I do, I've got a buffer. If I don't, no, I don't have a buffer. Okay, so let's say they want us to calculate the pH of a buffer solution, like this example problem. So the question is, what is the pH of a buffer that is 0.12 molar in lactic acid? And then they give us the formula for that, and 0.1 molar in sodium lactate, and then they give us the Ka for lactic acid. Well, if you remember when we did the pH of salt solutions that had a common ion, I guess it wasn't really a salt solution, it was a weak acid or a base that had a common ion added to it, that math is identical to the math here. So we can do this one of two ways. In this video, I'm going to show you the way that we've already done it, and then I will change it later. So let's go ahead and write the shorthand version of lactic acid, and we'll say that's in water. It's a weak acid, so it's equilibrium. The acid will be a proton donor, so we are going to get the lactate ion and hydronium. And then I'm going to set up an ice chart, not including water because it's a pure liquid, and I'm going to fill in what I know. 0.12 molar lactic acid and 0.10 molar lactate. Now, no hydronium ion before these two start interacting with each other. Okay, if I write the equilibrium expression, I will have the lactate ion times the lactate ion concentration times hydronium ion concentration divided by concentration of lactic acid. So because I actually have a Ka, 1.4 times 10 to the negative fourth. I can go ahead and use x up here in our ice chart. So if I do that, the 0 is on the product side, so the product side will go up by x, the reactant side will go down by x, and I will have 0.12 minus x, 0.10 plus x, and x. So I will have 0.10 plus x times the quantity times x divided by 0.12 minus x. Okay, if I take Ka times 100, I will get 0.041, which is 1.4 times 10 to the negative 2. That number is less than our initial concentration, so it's okay if I approximate. So what that means is that that x will be 0, and this x will be 0, because in comparison to the number that they are added to or subtracted from, they are so much smaller that it's basically going to be the same number. So instead, I now have 1.4 times 10 to the negative fourth equals 0.10x divided by 0.12. Okay, so when I take 1.4 times 10 to the negative fourth times 0.12, I get 1.68 times 10 to the negative fifth. That equals 0.10x. If I divide both sides by 0.10, I get 1.68 times 10 to the negative fourth. That is telling me the concentration of the hydronium ion. I could find the concentrations of the others if I wanted to just substitute this 1.68 times 10 to the negative fourth into both of these, but it's not asking me to do that. So I will do pH equals negative log of that number that I just calculated, the 1.8 times 10 to the negative 1.68 times 10 to the negative fourth. And when I do the negative log of that, I get 3 point checking sig figs. I have 2 here and I have 2 here. So my answer will have 2 numbers past the decimal. So it will be a pH of 3.77. Hopefully this looks identical to our calculations with a common ion because it's really the same thing. Whoops, sorry.